You stalwart, all spacey-ish, considered people. How many of you people come regularly to All Space Considered? How many of you got all confused because it's not the first Friday of the month? Right? Yeah, I know.
You're not supposed to be confused.
Yeah.
I
almost took the night off.
So welcome everyone, and thank you for coming on a weird day and putting up with the traffic problem. I think some of you know there was an emergency up here. Someone had a fall and roads were closed until just a little while ago. So it's been a weird afternoon, and so we're just going to make it weirder, right? Isn't that the thing to do? Yeah. Hopefully in good ways, because we'll try to bend your mind a little bit about how amazing and astonishing our universe is, and in particular, we have some guests tonight that are going to talk about a near 20-year legacy of research with a large space telescope launched by NASA, and we're going to hear all about that. But I'll come to that in a minute, because this is sort of an off mid-month All Space Considered. We usually say, today's Friday, January 17th. We usually say it's the first Friday of the month, but this is clearly not the first Friday, and there's going to be another exception coming up in a few months, so I'll tell you about that in a minute. But we're going to have the format also a little bit different this time, and the program's going to be a little shorter this time, sort of. So let's tell you what this is all about. I'm going to go through this first, and then we'll get to the logistics and the songs and swag and all the rest. But just so people can get oriented, so we can get oriented, that we're celebrating today the Spitzer Space Telescope. And we have here a poster of one of the beautiful results of the Spitzer Space Telescope of the plane of our galaxy and all the stars that are being formed toward the center of our galaxy. And our guests have a book that they're going to be talking about, and then we will break a little early so there can be a book signing. So it's not our usual format, but hopefully we'll always try something new. We'll see how that goes. So in the first half hour, we're going to talk about a couple of stories that you probably have heard about and may be wondering about. Stellar fainting spell. How many of you already know what that might be? We always talk about the Super Bowl of astronomy, the big meeting of the American Astronomical Society. But lately, since we talk about it usually in March now, not February, not at Super Bowl time, it's really now the Golden Academy Awards, or Golden Griffies of astronomy. Parker Solar Probe released results right at the time of last month's show, or December show. Then it didn't make it into that show, so we're telling you about it now. A couple of things having to do with commercial launch services, a big, interesting launch tomorrow morning. Some headlines from Mars, and our mini sky report, because it's only half the month, and some pretty pictures. Then we will bring up our guests who are joining us tonight to talk about the Spitzer Space Telescope, Mike Werner and Peter. I guess you don't go by Pete, do you? I called you Peter. Okay. Eisenhardt, who are both working with the Spitzer Space Telescope. And then after they talk for a little bit, we'll take a break around 8:45, go for the book signing. But we will remain, and so that people can get their books while the bookstore is still open, and have informal discussion afterward as opposed to prepared thing. We just didn't want to interrupt the book signing, and we didn't want to keep our colleagues at the bookstore too late, because they close at 9. So that is our intro. So let me turn now to a couple of housekeeping items. First of all, if you need to leave, the best way to go out is out the back. In fact, it's the only way to go out, because that takes you to a closet, and that takes you through an emergency exit. If there were to be an emergency, we will guide you out, but you will not make it on your own. So don't go that way either. In fact, I think the door is locked. No, it's not locked. Can't be locked. Right.
But you might end up in the depths of space again, and then
Yeah, that's true. You would get, yeah. Anyway, so go out the back if you have to go out the back. You can keep your cell phones on, but there's no signal in here, so they'll roam and roam and roam and lose battery. So you might as well turn them off, because you don't want them roaming and losing the battery. I also just wanted to acknowledge and thank those people that make it possible for us to be here. Friends of the Observatory is our membership organization associated with Griffith Observatory. And how many of you are photo members? A number of you are. We love our photo member friends. Thank you, photo members. And then finally, we like to thank the tax-paying citizens of the City of Los Angeles, because Griffith Observatory is owned and operated by the City of Los Angeles. And so your tax dollars at work make this amazing facility available, not only for everyone in Los Angeles and all the visitors from around the world and all the movies you see it in. So it's all a gift of the Griffith Trust over a century ago, and we're still here. So, with that, why don't we turn to Bill? Explain to us what all that music was about when we first.
Yes. Hi. I think a lot of you are probably some of our regulars, but for those of you who aren't, we always play a little game when we have our show, our All Space Considered show. It has to do with the music that you heard when you were walking in. We call that our walk-in music. And each piece of music is tied in some way to one of the stories that we're doing tonight. And when that story comes up, you shout out the name of the piece of music or some identifying component of the music, and you win a prize. And at the so at the end of the show tonight, when we're all done, I'll hand out the prizes to the people who rudely interrupt us by shouting in the middle of the show. Just kidding. Now, this is all Spitzer Considered, and literally all of our prizes are all Spitzer. It's an all Spitzer music game tonight. This is a poster of the infrared sky that we have that was done by Spitzer. And we actually have at least one copy of that poster as well, if you prefer the blue one. We also have all kinds of stickers for the mission. We have these beautiful, these are rulers. We also use as bookmarks. They have Spitzer imagery on one side. And the nice thing is they have inches for us Americans, but when we're smart enough to convert to the metric system, it's right there also. So that'll be good too. And I also have enough pins that everybody who wins tonight can get a pin. In fact, I have enough of one of our kinds of pins that everybody can get a pin for Spitzer if you would like. So even if you don't guess the song right, come on down, we'll get you a pin. And I cleared that with our scientists also. So, all right, thanks very much. Good show.
And no pen numbers. Okay. So if you've been to All Space before, you know we like to start with a launch, and this is kind of an unusual launch. Does anybody have any idea what we're looking at here? Except you two. We don't want to hear from you two. Anybody? It is a space launch. It's the launch of the Spitzer Space Telescope, and it's imaged in infrared. So that is the heat signature, infrared radiation coming off of the launch of the Spitzer Space Telescope, which is what makes our show special tonight. So we thought we would show that kind of different looking launch that perhaps you've not seen before. We've already covered this, the book signing at the end of the formal part of the program, and then there will be more informal conversation as needed. All right, so let's start with this familiar star pattern. It's been in the news a lot, and do any of you know why? Anybody noticed yourselves? That's right. There's a star in that constellation of Orion. Patrick, do you want to tell us what the big news is about Betelgeuse? What? Oh, I clicked the wrong one. Betelgeuse.
Yes, so how many have seen Betelgeuse in the sky? Okay, and how many of you have looked at recently and compared it to other stars? Okay, so it
You
is.
look kind of bored with it. Yeah, I looked at it.
Well, it looks nice and bright in this image, but this star has actually visually faded to almost as bright as its star next door, which is called Bellatrix. I went out Sunday and took this picture with my cell phone, and you can see that just from the brightness, from the diameters of the stars, Betelgeuse and Bellatrix are almost identical. We have some pictures here. This is a picture taken by amateur astronomers showing on the left, picture taken in, I think it's in 2016, and a picture taken just recently, and you can see the difference in brightness.
So the headline that they have on there is the fainting, and we all laughed about the fact that we've always heard of dimming. I mean, has anybody ever used that phrase, the fainting of something? But it seems to be what everybody's using now, so of course that made us think, oh, poor Aldebaran. Poor Betelgeuse has a spell. But anyway, so Patrick,
Right. Yes.
how can we know?
We're going to talk about how that fainting spell went for Betelgeuse. In fact, in order to express brightnesses,
Oh, no. You didn't know about that.
I did not know about
Yeah.
that.
Well, you
to the
said
slide?
you said Betelgeuse 3 times.
Yeah.
Oh, okay. Oh, that's the spell. Betelgeuse.
If you
Okay,
say it 3 times, yes.
okay.
For those who don't know, and I didn't because I didn't watch that, but apparently if you say it 3 times, he shows up. Yeah. So
Nice.
we just liked putting Patrick in the makeup. So Patrick, you didn't notice, but that was you
I
up
did
there.
not know.
Yeah.
No.
Okay.
Very surprising. All right. So where was I? Oh, okay. Yes. So in order to quantify brightnesses, we have a magnitude that astronomers use. They use a magnitude scale, and so on that night, on Sunday, Betelgeuse was 1.5, and Bellatrix is 1.6. Well, what does that mean? Well, we can summarize quite here with a magnitude scale. And the magnitude scale is kind of backwards. If you look at that number line, you see that negative numbers correspond to very bright objects, like the sun is negative 26.8. And if you go all the way to the right to Venus, it's minus 4.4. And then you get to Betelgeuse, and you notice there's a range of brightnesses. And that's because Betelgeuse isn't a star that shines with a constant brightness. It's a semi-regular variable star, so sometimes it's bright and sometimes it's dim. So you can see it's 0.2 to 1.3, which is the norm for this particular star. Now, the next this image shows you how much the brightness has changed. If you look at 2019, and the vertical scales shows you a magnitude, so all the way down is fainter. It was about at the beginning of 2019, it was about 0.9, and now on the right there, you can see that sharp dip right there. That was noticed from December, and it's down here, way down here, roughly about 1.5 magnitude. So it's it's dimmer than normal. And
We're going to get there. So let's keep
Yes.
going. In fact, let's
Yes,
look at
indeed.
this historically.
And you can see that the dimming is very deep compared to what we normally experience with Betelgeuse's minimum. And this actually caught the attention of astronomers at the AAAS, showing that this graph here shows that it's the faintest in 50 years. There's also a note there saying the ultraviolet is strengthening according to HST and STIS. So this also led to many headlines that you've probably seen. Is this star about to explode? What's
How many
going
of
on
you have
with this?
seen that on social media? It's going to blow. We're all going to, yeah. So it's been a bit of a headline grabber through the holidays and into now. And so that does beg the question, is it going to explode, and what is truly going on with that star? So this is an image of Betelgeuse. And Betelgeuse is, it's astonishing. When I was a kid, you couldn't image stars. They were just pinpoints of light. This is taken with the Alma telescope, and you can actually image the star now and see features related to it.
Right.
So, Patrick, can you tell us a little bit more about the star?
Yeah, this star is truly amongst the giants. It's called a red supergiant, and it's actually pulsates. So when it's at its largest and it's cooling off, its surface can actually extend out to the orbit of Jupiter, and then when it contracts, it's out by the orbit of Mars, and it's roughly about 20 solar masses. So it's a large star, and
Yeah, and I think the pulsation part about it too is that so it's very, as you said, semi-regular. And one of the theories as to what this is that there are different time scales for different pulsations. And one of the thoughts is that this is just when several of those different cycles are all at their dimmest. But it's still, as you can see historically, it's been this dim before, but this is not for 50 years. And so this is dramatic. So, David, tell us a little bit about red supergiants and what's going to happen to them.
Red supergiants. Well, they're a very large star. Sun, of course, has one solar mass, Betelgeuse, somewhere, some folks say set 10, others say 20. So there's a range of masses that people think it may have, but that puts it through its evolution. By the way, this is a chart of luminosity or brightness of stars, and then temperature. Things on the left are very hot and blue. Things on the right are cooler and red, and the sun is in the middle-ish here. We're right there. Now, Betelgeuse isn't a giant, which would be a star like the sun that's dying. It's way up there that's been circled. It is a supergiant star. So it has enough mass. Now it has evolved off that line, that diagonal line you see, where stars spend most of their life, where they're converting hydrogen into helium. Well, Betelgeuse is so large, it's converting heavier elements. In fact, its core will eventually be completely made of iron, and that iron can't be turned into anything else, and it's going to, well, at that point, it'll explode because the core can't do anything to itself to provide more energy. It'll collapse. The iron actually gets disassociated with, takes some of the heat away, which increases the speed of that collapse. So that core collapses catastrophically. Material probably rebounds somehow back out. A shock wave proceeds outwards, destroying the star. And in that destruction, a whole bunch of heavy elements are actually created. And this would be known as a type 2 supernova. Now,
So, I was just going to say, so is it going to explode? And if it is, what will it look like in the sky? Like that? So,
That's right. It's estimated that if it does do this, it will be almost as bright as the full moon, but all the light is concentrated in a tiny point. It'd be like looking at a arc welder's torch. It's just be. I think we would have to wear those specially made Betelgeuse filters to see
Betelgeuse
this.
glasses. So, yeah, it would be visible in the daylight. It would be a dramatic sight. So what would that do for our exhibits?
yeah, we'll have to think about redesign. The big red star in the corner there represents Betelgeuse, although it's smaller than its actual size. It should be at 1.5 times the size of the room, but maybe we'll remove it. Maybe if it's 20 solar masses and things go just right or maybe wrong, it might turn into a black hole.
When will it happen? That is the question.
We don't know. Sometime in the next thousands of years, probably. But tomorrow is within the next 1,000 years. So
Yeah,
we
you'll
don't
see
know.
people in the media saying, well, in the next 100,000 years. I've seen that quite a number of times. But it's really any time in there because we don't know and we don't have the predictive ability because catching these things before they happen isn't something that we do very often. Quick question.
How quickly will it collapse when it's in its final collapse? I mean, from there's a star to where to go.
Well, it'll get very bright. And if it completely turns into a black hole and goes away, it may disappear. But a type 2 supernova explosion producing a neutron star should become very bright, and it would be bright for a couple of years probably.
But the collapse itself is seconds or less.
Yeah.
It just goes. So very dramatic. Turning to another couple quick headlines, maybe you saw, we thought we could not avoid just mentioning that the TESS mission that David usually talks about has found its first its first Earth-like planet in a habitable zone. In other words, in a region of a solar system where life could happen. So that's a cool story you might want to look up. And also from TESS is a cool result of, and because of how many of you saw the Star Wars movie that's out? Come on, this crowd? No, all right. So they are calling it a Tatooine system. But this one's also been in the news a lot because it was the one discovered by the kid 3 days into his internship. So that's kind of fun and cool. Another major story that you might have seen last week or so is that the last decade is the hottest ever measured, and 2019 was the second hottest year. Also from Big Story, we just wanted to mention and suggest you can go look at some of this if you want to see, and that is that the Australia fires that have been in the news so much have created so much smoke. This is, of course, an aerial view, that the smoke, which is seen there in blue, well, this yellow batch coming off the fires, has now circled the globe. And so we've got Australia fire smoke everywhere around around the globe now. So it's kind of a fascinating thing. But these are stories, the main stories, as I mentioned, are all really coming out of the American Astronomical Society meeting that happened in Hawaii. So David, you want to tell us about that?
Yeah, it was a meeting.
The Amazon rainforest been on fire for a couple years?
There are plenty of fires in the Amazon rainforest, but this Australia, I saw something that said that, and this is a key thing, the carbon dioxide released by just these fires, this last round of fires in Australia, is equivalent to the total emissions per year of the 111th, I think, or 116th lowest emitting countries in the world. So it's a feedback thing. Increasing heat leads to more fires leads to more CO2. So anyway, go ahead, David.
Yeah, the AAS meeting, which is the American Astronomical Society, was held in Hawaii, which would have been great to go to, fun place to go. But of course, that meeting means it's time for... Yes, hooray for Hollywood. Whoever yelled that out, come after the show and get a prize.
And who was, Nancy Sinatra sang that in that version.
Yeah. So, of course, the Golden Griffith Awards, or the Golden Griffies as we call them, we base it off the AAS meeting where there are press releases and all sorts of topics are covered. We let you vote on which ones we are going to cover in depth, and people get prizes, all sorts of stuff. This is kind of what it looks like. But next month, you can come on back and you can vote to have us decide what you're going to hear about. It's a lot of fun. But at the AAS meeting itself, there were rainbows, of course, in Hawaii over the convention center, beautiful press releases all about that test planet that was found, the first Earth-sized planet in a habitable zone. Talk of clumps of dark matter, but clumps that are too small to make galaxies that they're seeing with these quasars. The SOFIA Airborne Infrared Observatory looked at the galactic center down below and then also the Swan Nebula, although there's some Spitzer data in that upper right image as well. The Large Synoptic Survey Telescope was renamed after Vera Rubin, the astronomer that helped map out the rotation curves of galaxies and provide evidence for dark matter. This galaxy she observed, actually, and it had never been observed with Hubble, so there was a Hubble observation of this that they released and talked about. And it's a very large spiral. It's unusually large. Lots of Twitter posts of blue drinks. Lots of astronomers drinking blue drinks and having a good time. And they renamed it the Neptini, even though it's a blue Hawaiian. And then also the Neptini evidently is the nickname for sub-Neptune-sized planets by some of these exoplanet astronomers. And I think they were probably drinking a lot of Neptinis when they came up with that idea. The Kepler mission that finds a lot of these sub-Neptunes cost about the same amount of money as the movie Avatar, it turns out. So the cost of movies is rising, and the cost of space missions, as you can see, has maybe dropped a little bit, actually. Talk of mega constellations, we've talked about those at All Space Considered, and Elon Musk just launched another 60 of the Starlink satellites. So astronomers are worried about what that's going to do. That Vera Rubin telescope, actually, it turns out those Starlink satellites will saturate the detectors. That's not a good thing, by the way. You don't want that to happen. There was talk about how do you tell apart labradoodles from fried chicken, and can you teach artificial intelligence to do it? Evidently, AI had trouble telling differences between fried chicken. This was part of a talk about the Event Horizon telescope that saw the black hole down at the center of M87 and how they were trying to teach it to recognize what it was seeing, and some of that has to do with pattern recognition. So all sorts of interesting stuff at the AAS, and of course rainbows. But first of all, come on back next month or come see us if you're watching on the internets, on YouTube or whatnot. Come in person and you can vote, and you can maybe take home one of these if you're lucky in March. So you can come back in March and be part of the show.
So I mentioned earlier we have a little bit of a different schedule. Today is not the first Friday, our All Spitzer Considered. Our next All Space Considered, we have a couple of astronomers from Caltech involved with the Cosmos Survey. It's a big, deep Cosmos survey field. And I, a year ago, went on an observing trip with them. And so we took some video, we cut together a small little movie about what it's like to go observing, and they're going to be with us, and we're going to talk about that. March is the Golden Griffies. And then the April show is also not going to be the first Friday, because the following weekend is the 50th anniversary of the Apollo 13 mission launching. And so rather than do two back-to-back, we just don't have the time to with people's travel schedules. So we're going to merge All Space Considered with the Apollo 13 commemoration as well.
Jim Lovell going to be invited?
He's always invited, but we do not plan that he'll be here. But one of the engineers who was with us on Apollo 11 will be with us, and he will be talking. He was in that back room solving problems real time. It's actually a great story, and I hope you'll come for that. These are our friends from Caltech. And then a little move of shameless self-promotion. I'm giving a talk on January 27th here as part of Friends of the Observatory's Cosmic Musings series. And I'm also giving a talk this Saturday. It's at the, it's on art and science, and with this lovely photographer, David Maisel, as part of the Forest Lawn. If you didn't know they have a museum, they do. So that's next Saturday, and please come if you wish. So tell us a little bit about, and we have very few minutes left.
Okay, yes. So Parker Solar Probe, first science results were released last month. Here's its orbit. It has actually gone around the sun 3 times, and past the last time was September 1st, about 15.4 million miles. The next time it will pass close to the sun will be January 29th, a mere 12 million miles away. The results were very interesting and had solar physicists very excited. A lot of its animation. So here is the solar probe is designed to study the corona and its magnetic field, and you can see those magnetic field lines coming out like that in a kind of uniform and curly fashion. But what they found from solar probe was those magnetic field lines are not exactly as smooth as they think. It actually has some flips in it, and when the solar probe flew through those magnetic lines, they actually found that they're actually kinked in different shapes, and that these flips in magnetic field occur in a matter of seconds. Also, our solar system is filled with cosmic dust from ancient collisions of asteroids and comet dust, but there's a region around the sun which is actually clear from the sun out to 3.5 million miles, and the thought is that the radiant heat of the sun is vaporized into gas, the dust around the sun. This is from the camera on board solar probe, and it's looking out, and you can see some of the solar wind is not exactly kind of straight or uniform. It's very turbulent. Another thing solar probe found was that when it's close to the sun, it can actually see small erupted events, particle bursts, that are virtually undetectable here on Earth. But by the time they come to Earth, it's kind of blended in with the rest of the solar wind. But it's important to measure these because it affects satellites and astronauts. And the last thing is this interesting picture from the camera there. That red line and that faint line in between is the trail of a dust trail from an asteroid called 3200 Phaeton, which is the parent body for the Geminid meteor shower that the Earth plows through December 13th and 14th every year. So it's very exciting, and there's more to come.
Now, I mentioned earlier that we'd have a few quick headlines about commercial launches. As you know, most of our space transportation has been with the shuttle for many, many years, and that's how our astronauts got to the International Space Station. But as most of you also know, the space shuttle was retired and is having a lovely time in Florida. So we've been dependent on the Russians for launch services to get to the International Space Station. So we've been very keen not to be dependent on another country. And so NASA gave contracts to SpaceX and to Boeing to develop crew capsules for launch services to the International Space Station. So 2020 is the year when they should be bringing, did I hear somebody call a song?
Boing.
Boing, boing, good, good. To the International Space Station. And here are some of those brave astronauts that will be the ones that fly the first missions on these 2 new spacecraft. So this is a quick summary of their schedule. The main thing to see is the SpaceX in green, and the Boeing ones on the right are in orange. I'm going to mention very briefly, the Boeing had a test. It was launched and landed successfully. So we'll let this...
And liftoff, the rise of Starliner.
The rise of Starliner. So it had a successful launch, it had a successful landing, and just because Brendan, who made this, that's the CEO from Boeing, and there's the competition, so I just had to put that in there, was that it did not make it to the International Space Station. They had to, there was a clock error. The mission thought it was 11 hours ahead. And so when the mission clock on the spacecraft took over, oh my gosh, I'm in the wrong place. I got to go over here, fired its engines, spent too much of its fuel in order to raise its orbit later to the International Space Station. Everything else worked fine. All of it landed, it even did its docking maneuver, but just didn't dock in terms of sticking out the docking apparatus. But it did not fulfill the mission objective of getting to the International Space Station. So that may have an impact. Right now there's a 2-month study going on with NASA and Boeing trying to figure that out. And one of the big questions that is being asked is, do we need another uncrewed test, or should we go ahead and launch the astronauts? It's a fascinating question because, as they say, shuttle never had uncrewed tests. It was always crewed. When you think about what Apollo did, they just put people on there, hey, go to the moon. But it was kind of crazy. They were way out there on the risk level. So I think it's a very interesting thing about what is going to come. The other thing I want to point out is tomorrow morning, a very exciting launch of a SpaceX crew vehicle and trying an abort process in case there were to be an accident during launch. Could the astronauts get home safely? So let's just say it's on purpose and nobody will be harmed in it. So when you see the thing going wrong, if you watch it, it's not because it's bad, it's because it's supposed to go wrong. And there's no crew on board, so no one's going to be hurt. It's just to test this. And this little diagram shows it. It launches. And then at max Q, which is the highest dynamic pressure on the vehicle, they simulate if there were to be a problem, can we jettison the astronauts and make them safe? So the launch window opens at 5 o'clock in the morning our time tomorrow. Today's reports as of an hour ago say that it's windy and it'll probably be toward the end of that range.
So very quickly, some headlines from Mars. Mars, as we know, has polar caps and water. Well, some folks have mapped out where we might be able to dig water ice from close to the surface. They did this by mapping out temperature differences right above the surface. Turns out that the ice underneath can affect the surface temperature, keep it a little warmer than it should be or a little cooler. We've seen ice below Mars before. It gets unearthed during craters as they happen. It's there, then it disappears later, which says the ice is subliming. We've seen it in the walls of cliffs. But they correlated those together. They correlated where the temperature was different right above and where they're seeing the water ice underneath, and they match fairly well. And that's why they were somewhat confident to say, let's go searching sort of right in this region. And sure enough, the Phoenix lander that dug up ice underneath is right above where they think is a good place to go get water. Water's important because it can give you rocket fuel. You can break up the water, the oxygen and the hydrogen, use the hydrogen for rocket fuel, use the oxygen to breathe. So it's a good thing if there were ice underneath these Martian explorers.
And that was the skater's waltz.
Yes.
Okay, in a
Yes.
minute.
Mid-January sky report. So you can see in the evening sky, if you look to the southwest, Venus. This was a picture taken last month with the moon right beneath it. You have another opportunity to see this similar on January 27th. And in the evening sky, of course, our winter favorites, Orion. We talked about Betelgeuse.
A little too bright.
Yeah, it's too bright, yes. And you can use the Orion's belt to find Sirius and a star way below there to the south called Canopus.
It's Patrick's favorite star.
Yeah, it's my favorite star because I've never seen it before. But you can only see this if you live less than 37 degrees north latitude, so the south of it. So there you are. Here's a picture I took, and you can do the same thing. In the morning sky, you see the moon and Mars and Antares all together, a nice little bunch there. That's on the 20th, and Jupiter's just about rising from the southeast. Quick look at our moon phases. We're last quarter today, new moon's a week from now. And here's our February calendar. We'll talk a little bit more about that next month.
And our star party is on the 1st of the month.
That's correct, yes.
So with that, let's dim the room. We're going to do some pretty pictures. It's okay to keep going, Matthew. I realize we didn't talk about that, but the live stream audience will keep with them because we want them to stay with us for the Spitzer talk. Often we turn off for the photographs, but we're going to go for it this time. So lights out, down, and
It's a beautiful galaxy. We're seeing some hot young blue stars in there. Icelandic volcano that's beautiful and green.
it looks like the one on Ceres to my eyes. And speaking of volcanic mountains and pretty pictures,
And it's sort of a flocculent spiral with star-forming regions and young stars and a beautiful glowing center.
this is a beautiful image of the recent meteor shower. I can never pronounce it.
Quadrantids.
Thank
Quadrantids.
you. Listen to him.
And I was really into spiral galaxies this month, I guess, and this one is more edge-on. You can see this beautiful dust lanes blocking out the light from the stars behind.
This is the annular solar eclipse that happened over the holidays. And here's a shot of I love what the horizon did to the sun during the eclipse. Yeah. And then our last in this series, this is the eruption of the volcano in the Philippines. Sped up, of course, but you've heard Patrick talk quite a bit about the lightning that can be generated during volcanic eruptions, and what an amazing sight. It is sped up, so. And then we wanted to finish our pretty pictures as way of introduction to our guest with pretty Spitzer pictures, because if there's one thing, well, there are so many things that Spitzer can do, but it really takes pretty pictures and gives us a new view on the universe. I know our speakers are going to tell us about this, but these are all just to enjoy for their sheer beauty. All pictures from the Spitzer Space Telescope. Our speakers will tell us some of the amazing things that these pictures reveal, but these are just to appreciate. It's a lovely work. I guess a lot of it's been Robert, hasn't it? Yeah. This is a crazy one. Love that one. And this coronet star cluster, very nearby, beautiful. And this is our last one. So with that, let's bring up the lights and let's bring up our speakers and trade places. Please go ahead.
Do volcanoes add a lot of CO2 to the atmosphere?
They add CO2 to the atmosphere, yes, but I do not believe that it is anywhere comparable to the man-made sources.
Much, much smaller.
Yeah, that's a fraction, I believe. So, thank you, Michael and Peter, for joining us. Oh, and yes, prop. Get this lovely book in our bookstore, More Things in the Heavens, which is about the Spitzer Space Telescope and the amazing things you guys have learned and the journeys of exploration that you have taken by being able to see what Spitzer sees. So let me hand that back to you so I don't steal your copy. But why don't we just go right ahead, and why don't you tell us all about the Spitzer Space Telescope?
Hello, everybody. I'm Michael Werner. I'm the project scientist for the Spitzer Space Telescope. I've actually been working on this project for 43 years, if you can believe that. I'm delighted to be able to tell you about Spitzer and about our book. I'm here with my colleague, Peter Eisenhardt. It's always a pleasure to speak to people about astronomy, and I'm reminded, just a personal note, that after the Loma Prieta earthquake in San Francisco 25 or 30 years ago, when the Bay Bridge pancaked and it was a dark and stormy night, I was speaking at the planetarium in Golden Gate Park, and there were hundreds of people there to hear me. I mean, not hundreds, a goodly crowd, and that just reminded me of how interested people are in astronomy. I'm well aware of the fact that we work for you in this business, and I'm pleased to be able to tell you about what we've been able to do. So here you can see a picture of, whoops, I'm sorry, a picture of the
I can get you back. I'll do it.
Great Observatories, which was a concept developed in the 1990s to have observatories working across the entire spectrum. This is what was called CERTIF at the time. It's now Spitzer, working in the infrared. In visible light, we have Hubble. In X-rays, we have the Chandra Observatory. And again, the Compton Gamma Ray Observatory. it hasn't, that was not even a gleam in its pappy's eye at that point. But in this wavelength region, it would be here, bridging the gap between Spitzer and Hubble. This shows the atmospheric transmission. Of course, much of the infrared is blocked. It also shows the fact that the thermometer at the bottom. And all objects in the universe radiate at a wavelength which is dictated by their temperature. And cooler objects radiate in the infrared, warmer objects in optical light like the sun, and still warmer objects, energetic things like supernovae might radiate X-rays. You also see the...
Mic flipped under.
Oh, sorry.
Or that, or it fell off. It fell off.
Okay. You also see the wavelength scale at the bottom, and we measure wavelength, which is the distance between the peaks and the waves in units called microns, where 1 micron is sort of the boundary between visible light and infrared light. So you can sort of see here that you might see different things in the infrared than in the visible, which is why we need this family of telescopes. And that's illustrated very nicely here by our dog Rusty. So Rusty is an ordinary dog. The lower image is the visible light image of Rusty. In visible light, what we see is scattered sunlight or scattered room light. If you turn the lights off, you don't see the visible image. The infrared image at the top, we're seeing Rusty where the radiation is indicative of the temperature of Rusty at various regions. And so you can see that near his eyes and his mouth, closer to his blood supply, be a little bit hotter. And from the temperature scale on the right, you can see that corresponds to more infrared radiation. And where his fur is very thick, like towards his tail, it's cooler, and you see less infrared radiation. And since Rusty is a proper dog, he has a cold nose. Okay, so things look different in the infrared than in the optical part of the spectrum. That picture was taken with a night vision camera, perhaps, or with a infrared camera similar to the ones that were used on the Spitzer Space Telescope. So when we look at the infrared in terms of astronomy, there are several principles which we exploit in giving the unique characteristics of the infrared part of the spectrum. One is, we call this the old, the cold, and the dirty. That's a previously unreleased Clint Eastwood movie. But the old refers to the fact that because of the expansion of the universe, light is stretched. In more distant objects, the light is shifted further and further out into the infrared. So the visible light from very distant objects comes to us in the infrared part of the spectrum. That's illustrated here. When I take an optical image on the left and add to it an infrared image, you see this, that's called a cluster of galaxies. A bunch of galaxies clustered together by gravity, clearly seen in the infrared because of the fact that their light comes to us now in the infrared. That's way more than halfway across the universe that we're looking to see this cluster, and Peter will be talking more about this later on. The cold refers to the fact that things which are too cool to radiate an optical light, like our sun radiates optical light, it's at a temperature of 5,000 degrees Kelvin. Here you see the red, this is a picture of what's called a planetary nebula, which is a late stage of stellar evolution where a star like the sun has shrunk to a cosmic ember called a white dwarf, and in the process puffed off a cloud of gas and dust. And around that star, we see this red bubble on the right in the infrared image, which is produced by radiation from dust, puffed off by, this is dust is probably the remnant of a solar system around the star when the star was more sun-like, and is heated by the star to a temperature of perhaps 100 degrees of above absolute zero, plenty warm enough to produce a lot of infrared radiation, but not warm enough to produce any visible light. So that's the cold. And finally, we have the dirty, which alludes to the fact that cosmic dust, little tiny particles of sand and graphite, soot, organic materials, is a ubiquitous constituent of astrophysical systems. And this interstellar or circumstellar dust has the properties that it's opaque at visible light, but often transparent in the infrared. So this is an image of a region where stars are forming. Stars form out of dense clouds of dust and gas. In its visible light image, you can see there are lots of areas, particularly a little bit to the right and below, where you don't see much. But when we look at the same region in the infrared, sorry, I'm doing the wrong thing. You see, as the infrared images come up, you see all these stars there, which are not visible because of the interstellar dust absorbs their light in visible wavelengths, but you can see them in the infrared because the infrared light comes through, and we can see the stars in the infrared. At the same time, as was the case for that cloud of dust around the star in the planetary nebula, sometimes the dust is heated by starlight to a temperature where it can radiate in the infrared. So interstellar dust is a infrared astronomer's best friend. So going back one more time, visible light, don't see much. It's interesting enough. And here in the infrared, you see spectacular image. I might add now that most of the images we'll be showing you are images from the Spitzer Space Telescope. They were obtained at infrared wavelengths, which you couldn't see with your own eye. Now, the reason we convert these into the infrared is because into visible light. We take these infrared images and with well-established protocols convert them into visible light for three reasons. One is they're awfully pretty to look at. The second is you wouldn't be too impressed if I showed you a bunch of ones and zeros. And the third reason is that people who, as you grow more and more familiar and comfortable with what's going on in these environments, you can draw inferences about the nature of the processes and the conditions very, very readily. And here, for example, in the upper left, the red emission comes from a class of molecules called aromatic hydrocarbons that we'll be hearing more about, that are ubiquitous in space and that Spitzer has seen lots of radiation from. And those aromatic hydrocarbons are excited by stars on the main sequence, like our own sun. As you move down to the right, the objects we see in the infrared have more the character of young and forming stars still embedded in their natal cocoons. And so our inference here is that there's a wave of star formation propagating from the upper left to the lower right, where each generation of stars encourages or induces the collapse of the adjacent material, which then goes on to form another star, and so forth and so on. So this infrared stuff is pretty exciting, and you might say, well, why don't we throw an infrared detector on a big telescope like the Palomar telescope and let's go to town? And in fact, people have done that very successfully. I've done it myself. But when you do that, you lose sight of the fact that the surface of the Earth is a poor environment for infrared astronomy. And to do that, I've got this little story here. So these are pictures, in fact, of the Palomar telescope in the upper left. The upper left picture is taken in the daytime. You notice the dome is closed and the astronomers are asleep. The stars are still there, right? But you can't see them because the sky is very bright due to scattered sunlight. And that's what's shown in the picture day, this little cartoon here. Now next to it, there's a cartoon showing the brightness of the sky in the infrared during the day. And that's very bright because the sky is hot and the telescope is hot. And you're looking through the hot sky off of a hot telescope. You see a lot of infrared radiation before you have any chance of seeing anything outside the atmosphere. When you come back at night, you'll notice that the dome is now open and the astronomers are working and they're getting images like this, the Orion Nebula again with Betelgeuse in its excited state. And that looks pretty great in visible light. But infrared light, the sky is just as bright as it was during the day because it hasn't cooled off at all. So if you really want to do the highest quality, most sensitive infrared work, if you want to work at night in the infrared, you go into space and you cool the telescope. You're in space, you have no atmospheric emission, you can see the entire infrared spectrum, and the cooled telescope means there's no instrumental foreground as there is from a warm telescope on the ground. And that's what Spitzer has done, and that's what made Spitzer so powerful scientifically. The image there is actually an image of the Orion region from an earlier cryogenic infrared telescope in space called IRAS that you may have heard about. So now a quick introduction to Spitzer. I've sort of set the stage here. Here we go. So Spitzer, as I said, is NASA's, there's a picture on the left. It's NASA's Great Observatory for Infrared Astronomy. Was launched in August 2003, more than 16 years ago, into an Earth-trailing orbit around the sun. This is actually quite important. So Spitzer is not going around the Earth, it's going around the sun. And the reason we want to do that is because the Earth is a pretty major source of heat. And it's much easier to get your telescope cold if you're far from the Earth than if you're near the Earth. And in fact, because we're far from the Earth, and because we can always keep the telescope oriented so that the solar panel is pointed at the sun, we can use the back of the telescope as a big radiator, and it radiates into space, into the cold blackness of space. And that means that the telescope is cooled largely by radiative cooling. And when we ran out of the liquid helium we took to get us cold at first, it stayed cold. So here it says, cryogen depleted, warm mission starts. The green part of the trajectory, we had all of our instrumental capability with cold instruments. Here in the latter part, we're only using a limited number of instruments, limited measurement capability, but still able to do really phenomenal science. Here is the end of 2019. That's where we are. This picture is what you would see, I should have said, if you're fixed above the pole of the Earth. You just watch Spitzer moving away. And next month, the end of January 2020, less than 2 weeks from today, we'll be putting Spitzer to sleep. A bittersweet day, shall we say. The text on the left tells us Spitzer's an 85 centimeter cold telescope. It covers a wide wavelength range with both imaging and spectroscopy, can take pictures and obtain spectra. We use large detector arrays, kind of like your cell phone camera, a little more expensive and fewer pixels, but a big advance for the time, and that allows us to cover large regions of the sky very effectively. Spitzer is more sensitive, even though it's an 85 centimeter telescope, than would be a 10-meter telescope on the ground working at the same wavelengths. The impact of that reduction of the sky brightness is so profound that it allows us with Spitzer to do things that would otherwise be impossible. And as I say there have been almost 10,000 refereed papers based on Spitzer results.
Could you compare what you just described with what we'll expect with the Webb?
Yeah, I'll do that. I'll touch on that briefly. Peter will talk about it as well. But basically, the Webb telescope will have 50 times the collecting area of Spitzer. It will cover a wavelength range which includes some visible light down to about 0.5 microns and some infrared light out to about 25 microns. Doesn't go as far into the infrared as Spitzer did, doesn't go as far towards the ultraviolet as Hubble did. And in that wavelength range that it operates in, it will have instruments both for imaging and for spectroscopy. So it'll be very, very powerful scientifically. And we can talk more about that later, but that's a good question. That's sort of the view from 30,000 feet. Okay, so just quickly to go through a few of the Spitzer science results. Because of our large detector arrays, we're able to cover large areas quite effectively, and that's what's called doing a survey. So here on the left, this whole story is a survey of a region where stars are forming. The region on the sky is about 20 times bigger than the full moon, just to get you in the right frame of mind. On the left, we see a number of kind of shell-like structures which were carved out in the cloud of dust and gas within which these stars are formed by either exploding stars or very active stars with stellar winds, which are pushing stuff around. And unfortunately, you can't see it too well, but the little postage stamp in the middle is the famous pillars of creation from the Hubble Space Telescope to the same scale, because we see some of the same phenomena. The little box on the left, blown up to the right, shows in detail the positions of a number of young and forming stars which we found in this region. And you can see that the green symbols are young stars. They can be identified by their infrared signatures. Again, this is all in the infrared. The yellow symbols are really young stars, okay? And so my explanation of what's going on here is that there's a wave propagating downward where the stars which are producing these cavities are eroding the interstellar material and blowing it away. As they blow it away, they leave behind the stars that have just formed there, and that's the green stars. And in places where the material is more robust, like the mesas and so forth in the Southwest desert, it stays there, and the material isn't blown away, but instead the compression of that wind and maybe the adjacent stars induces the formation of yet another generation of stars. So if we came back in a few million years, the objects that are now colored yellow would be colored green. The whole red structure, red because of the hydrocarbon emission, would have moved down a little bit, and a new generation of yellow stars would be in place.
So we'll have that talk a million years from now on the last Friday of January.
I'm there. Yeah, sign me up. Okay. In a little more detail, we now know, because we know from the Kepler spacecraft, exoplanets are very, very common. You can bet that any star you see in the sky has got one or more planets associated with it. And those planets and that planetary system thus must form as the stars form. And that all takes place in a structure such as that shown here, which we call a protoplanetary disk. So as a star collapses in the interstellar medium, a cloud collapses to form a star. Because of the conservation of angular momentum or spin, a disk will form around that forming star, and that disk will give birth to a planetary system. We know that happened in our solar system because all the planets go around in the same direction, and they're all confined more or less to the same plane in space, which is the plane where that disk was 4.5 billion years ago as the solar system formed. Okay. I'm going to skip over the next slide, which just tells how we can determine the composition of this material. And in these disks, we see interesting organic and pre-organic materials. So we see the stuff of life, if you like, being incorporated into a new planetary system. And this is not at all unusual. Disks like this are seen around thousands of stars by Spitzer. Okay, can you move on to the next slide, Laura? Oh,
Yeah,
so,
you have control.
Yeah, okay. Now I want to talk about exoplanets, which is the big, exciting field of science which grew up with Spitzer. Spitzer's made major contributions to the study of exoplanets. The problem is shown here, where there's the sun and there's the Earth next to it to physical scale, not right distance. You can see that the star is much, much brighter than the planet. And so the way you find the planet, up to down for the most part, is by seeing the effect of the planet on the star. And one of the best instances of that is what's called a transiting planet. Because there are so many planets around stars, a goodly number of them have their orbit edge on as we look at it. And here's what we see when we look at the light from the planet plus the star edge on. There's the planet going around the star. In just 1 second, it's going to go in front of the star. And when it does that, that's what's called a transit. And when the planet transits the star, there's a brightness in the light from the star, which tells us something about the size of the planet. And if that occurs regularly enough, say every 3 days, you know there's a planet of this size in a 3-day orbit around that star. Using this technique, we with Spitzer were able to show that there's one star called TRAPPIST-1, because it was the first star found by the TRAPPIST survey, which is actually home to 7 planets, 7 Earth-sized planets. You know the size of the planets from the fraction of the starlight that they block. You know their position from the duration of their orbits. And from that, we know that at least 3 of these planets are in what's called the habitable zone, the region around a star where water would be liquid on the surface of the planet. And it's thought that that's a really prime place where life might conceivably form or have formed at some point. If I go on back to my little animation here, here's the planet going around the star. Now watch what happens when it goes behind the star. When it goes behind the star like this, if the planet is bright enough to produce its own infrared radiation, when it goes behind the star, that infrared radiation is no longer seen. And that drop, seeing that drop corresponds to seeing the infrared light from that planet. And Spitzer was the first telescope ever to see light from an exoplanet, from a planet around another star. Finally, as it moves towards what's called the eclipse, you can see that more and more of the star-lit side of the planet becomes visible. We think these planets are tidally locked to the star, and so here we go again. We're seeing more and more of the starlit side of the planet, and when we make those measurements and sort of unscramble them, we come up with something like this, which is actually the temperature distribution on the surface of that planet, okay? And to me, as I was saying earlier, it's easy to get jaded in this business. You know, we deal with amazing things every day. But to me, it's absolutely amazing that I can sit here with a straight face and say, look, that's the temperature distribution on the surface of a planet 40 light years away that I have never actually seen. Okay, I think that's just wonderful. And in this case, there's a displacement. The hottest point on the surface of the planet is not where those two arrows would intersect. That's the substellar point. That's the point where it's always high noon on this tidally locked planet. But the hottest point is displaced from that, and we think the reason for that is that the heat of the star, which falls onto the planet, is transported through the atmosphere of the planet by winds before that heat is re-radiated. So not only do we understand the temperature of the planet and the temperature of its atmosphere, but we can even make informed speculations about the character of the heat transport and the physical properties. This whole field of characterizing exoplanets is one that Spitzer has really pioneered and dominated.
Is that a Neptune or a Jupiter planet?
This is what's called the hot Jupiter. Okay, so it was one of the first and best, therefore best studied exoplanets. Finally, you were talking earlier about the James Webb Telescope. You might ask, what is James Webb going to do from the point of view of studying exoplanets? This figure shows the planned exoplanet observations by James Webb. Not all of them, but some that are already in the hopper, so to speak. The x-axis is the planet mass. You can see it extends from an Earth mass down here. Whoops, I didn't want to do that. Rescue me. It extends from an Earth mass down to at the far left to the mass of Jupiter here. And the vertical scale is the radius, or the temperature rather, which is as little as a few hundred Kelvin for the coolest of these planets, and then up over thousands of degrees for the hottest. There's quite a variety of planets, and this is only a very small sampling of the thousands of planets that have been seen. Those which are circled have been studied by Spitzer. So Spitzer is an important precursor for the James Webb Space Telescope observations of exoplanets. And finally, if we look in detail at the lower left segment of that picture, we see what we show here. These are planets now which are very Earth-like. Their mass is about the mass of the Earth. Their temperature is a few hundred degrees Kelvin, like 300 degrees Kelvin, as is the temperature of the Earth. And with Spitzer's pointing the way, with James Webb, we're on the verge of studying and searching for biological signatures on Earth-like planets around nearby stars. So that's the end of my part of the story. I'm going to transfer now from these very nearby objects to the most distant portions of the universe, which Peter will now tell you about another area where Spitzer has made major contributions. Thank you.
Thanks, Mike. It's really fun to be here in the Nimoy Theater at Griffith. It's just sort of awesome just walking into the. We had plenty of time, unfortunately, to admire it from about 100 yards away as we were waiting to get in. But,
Yeah.
I do want to emphasize something that Mike was touching on just there. It was an exciting time when we were planning Spitzer in the 90s, but it's even more exciting today, and Spitzer has a lot to do with that. And we're on the threshold of really being able to say if there is life beyond Earth. Maybe we'll find it on these exoplanets. Maybe we'll find it in our own solar system. But we're not. I don't think we're that far away from that. And similarly, we're not that far away from seeing the very first light in the universe. That's what this slide is meant to illustrate. This is a visualization of the history of the universe from the Big Bang to the present day. And so you see at the bottom of a couple of axes. One is time since the Big Bang, going from 0 right at the Big Bang up to the present day, which is 13.7 billion years after the Big Bang on the right, when galaxies such as our own and stars and planets and us are around. You also see a scale called redshift. And so as Mike was saying, the light that was emitted earlier on in the history of the universe expands along with the universe, and that expansion factor the amount by which it's expanded is called the redshift. And so if we look way, way back to only 300,000 years, 380,000 years after the Big Bang, we're looking at about a redshift of 1,000. Light from that time, 380,000 years after the Big Bang, has expanded 1,000 times, as has the universe since that time. Okay, so Spitzer's actually brought us quite close to that first light, and I'll say more about that in a minute. I've said all that already. And yes, important. So our main way of measuring distance to these distant objects that are not 40 light years away, not 100,000 light years away, but millions and actually billions of light years away, is by measuring how much the light has expanded, by measuring the redshift. Okay, I'll go over that again for anybody who hasn't quite got redshift yet. It takes a little while to get this. I know for some of you it's all that, but not for everybody. Okay, so let's start with some nearby galaxies. Laura, I think, showed this one, a slightly different color map here, but this is one of our very favorite galaxies, Messier 81 in the Big Dipper. A really beautiful spiral. These are Spitzer pictures, and what we're looking at here in blue light are the shorter Spitzer wavelengths taken at 3.6 microns and 4.5 microns with the infrared array camera. And then in the yellow and green here, we're looking at light that goes out to 24 microns with the multiband infrared photometer for Spitzer, originally for Certif. I have the Certif shirt.
I was going to comment. Your shirt, I'm going to interrupt long enough so now you've referenced it so people know what you're saying. The shirt says Certif, which stood for Space Infrared Telescope Facility, right?
Originally for Shuttle Infrared Telescope Facility, and then for Space Infrared Telescope Facility, cleverly. And then after we launched and were proven to be fully functional and didn't have any spherical aberration or any other problems, the Spitzer family agreed to renaming it after Lyman Spitzer, the famous astronomer who actually was essential to the development of the Hubble Space Telescope.
Yeah.
So what we're seeing here in blue is 3 or 4 micron wavelength light that comes from older stars, and it gives an idea of how much stellar mass is there. What we're seeing in the yellow and red is from younger stars, actually from the dust around younger stars, and we see these dusty star-forming regions strung out along the spiral arms. Mike likes to say like ornaments on a Christmas tree. It's really quite a beautiful picture. M81's neighbor is M82. Messier 82 is a starburst galaxy, and it is undergoing a tremendous burst of star formation. Here we're seeing in red those polycyclic aromatic hydrocarbon molecules, little dust particles that are being excited by ultraviolet light from forming stars. And those dust particles are actually literally being blown out of the center of M82 by a starburst, a very active starburst. And so it's thought that M81 and M82 interacted, and because of the relative spin of the two galaxies, gas flowed into the very core of M82, the one shown here, and caused this starburst, whereas in M81, the one I showed a second ago, it just sort of enhanced the star formation in the arms. And then here's another beautiful Spitzer image. Here we're looking at the Sombrero galaxy, Messier 104, I believe. And this is almost like a hybrid of two different galaxies, an old spherical bulge of a very massive galaxy, actually much more massive than our own, and then a star-forming ring, perhaps the result of a merging system.
So just to reemphasize, all that blue light is all stars.
That's right.
Because it looks almost like it's a vapor, but it's all stars.
Yeah.
If we could look with high enough magnification, we would start to pick out individual stars there. Now, if we look, one of the things that Spitzer could do actually was take images with its spectrograph in spectral bands, and that's shown in this image here. And that shows us that when you look in the wavelength of the polycyclic aromatic hydrocarbons, you just really see the ring, and that tells us that that ring is red. It's not just putting out continuum emission from warm dust, it's actually putting out the spectral features that are associated with those dust particles around forming stars. Okay, this galaxy is about 30 million light years away, but I'm going to now step out much farther. And before I do that, I want to explain where, remind you, I've already talked about this once, but let me say again where this light is coming from. So the black line here is the overall brightness distribution of a typical galaxy. You can see the wavelength on a log scale going from much shorter wavelengths than we see, 0.1 microns into the ultraviolet through to 1 micron, so that's kind of the visible range, then out to 10, 100, and 1,000 microns getting out into the infrared and even the millimeter wavelength range. And what we see is two peaks. This is the camel that has two humps. The shorter wavelength hump is the one that we saw in blue in the image of the sombrero a second ago. And that's coming from stars, evolved stars. And measuring the amount of that light tells us the mass of stars that's there. The peak on the right, which I think I can do this without disrupting too much there. So this one is coming from warm dust, and that is associated with forming stars. And Spitzer, you can see the Spitzer wavelength band kind of straddles both of these. The other thing that you see, let's see, so again, it's light from 1 micron coming from mature stars, telling us the stellar mass, the light from the longer bump coming from warm dust, and then the wiggles in the middle also coming from those polycyclic aromatic hydrocarbons that I showed the spectral image of a moment ago. And Spitzer has the ability to measure both of those. Now the red curve says, well, what if we put this galaxy far, far away, so far away that the universe has expanded a lot since that light was emitted. The light has expanded by 200% in this example. We call that a redshift of 2, 200% longer wavelengths than what started out.
So you're saying that's a galaxy far, far away a long time ago?
Yes.
Absolutely.
Exactly, yes, actually about 10 billion years ago. So,
Very good.
Is there a
Laura.
spectral signature of buns, hair buns? Please keep going. I apologize.
I don't know, there might be a Jabba the Hutt somewhere in there. But what you see is that the light from the stars, the bump on the left, try and do this there. This guy is really shifting into the Spitzer band, okay? And so actually these distant galaxies are in some ways getting easier to see as they get farther and farther away. And at the same time, it's dropping like a rock at these shorter wavelengths, which are the visible wavelengths that you look at with telescopes, optical telescopes like the 200-inch or Hubble. And so Spitzer is very, very powerful at looking at these features from distant galaxies. And that's, right, so this point is being made again here in words in case I forgot to say it. So obviously the further away the galaxy is, the bigger the shift is. And the most distant galaxies really can only be seen in infrared light. And I will show you an example of that in just a couple minutes. But here is a reprise of that picture that Mike showed. This image was taken with the Kip Peak 4 meter. It's about an hour exposure in optical filters. And then this picture on the right was taken in 90 seconds with Spitzer, which is not a 4 meter telescope. I think I saw somebody up there holding up their hand. It's about like this. So it's sort of a hula hoop size telescope. So, and it's this cryogenic telescope in space, but also the fact that the redshift is pushing the light into the Spitzer's band. So infrared is really crucial to seeing the early universe, looking back in time towards the first light. Here's a little more detailed example of a more distant field. If we want to look far, far back, the example I just showed was about 8 billion light years away. This is the Hubble Deep Field, which I'm sure is familiar to many of you, as seen with the Hubble telescope itself. Hubble exposed for about 10 days to get this picture, and because of this need for infrared light to see the most distant galaxies, astronomers worked really hard. David Hogg and his colleagues worked really hard to get an infrared picture from the ground with the Keck telescope. They spent about 10 nights trying to get this picture in the middle at infrared wavelengths at about a 3 micron wavelength. And, well, they saw a few things. It's, this is a negative image just in case you're wondering. So the black dots there are detections. Spitzer spent a few days looking at this, and this is what we found at 3.6 microns. And so I think you can see that the patterns are very recognizable at 3.6 microns. But Spitzer didn't just image at 3.6 microns. He also did 8, 16, 24, and 70 microns. And so with these measurements, we're able to measure both the amount of stars that there are in these distant galaxies and the amount of star formation. And that's really been critical for our understanding the history of star formation over the lifetime of the universe.
About Sophia?
Sophia can't do very much of this sort of thing. These objects are really too faint for Sophia to study. Sophia can study objects in great detail, but they have to be relatively bright. And Sophia is essentially earthbound. So this is as I was saying, Spitzer has been measuring the star formation history of the universe, and that's from measuring that longer wavelength light at 24 microns in particular. And Herschel has also measured that. Herschel is an infrared telescope that the Europeans launched in 2009, I think.
Approximately, yeah.
And it's a bigger telescope than Spitzer. It stopped operating in 2013, but it could go to somewhat longer wavelengths and carry these star formation measurements out a bit further than Spitzer could. And so with those measurements, we're able to assess how much star formation there's been going on versus the age in the history of the universe. So on the top of this plot here, we're seeing how far back in time. Let's try that again. There we go. Okay, so here we are today at 0 years from now, looking back 2, 4, 6, 8, 10 billion years, or in redshift 1 or 2. And 10 billion years ago, what we see is that the cosmic star formation rate was about 10 times higher than it is today. So the universe was really hopping 10 billion years ago. Astronomers sometimes say that we're in cosmic dusk today, and this peaked 10 billion years ago was cosmic high noon. And then an interesting thing happens. I mean, this is pretty interesting to start with, but then it actually starts to drop again, at least as best we can tell. Here we're limited more to measurements with optical telescopes because the redshifts are so large that even Herschel couldn't measure them. Nowadays, there's a millimeter telescope in Chile called the ALMA telescope that is giving us some idea of what's going on with star formation in the infrared at these very early times. Okay, the other thing to notice here is that that black line is just a mathematical approximation of the data points. It's just sort of take a simple mathematical function and say, okay, well, this goes through the data points pretty well, all right? Now we're going to look at the other thing that Spitzer measured, which is the stellar mass. Okay, again, we're starting with stellar mass today is about a little over 10 to the 7 in these units. Solar masses per million cubic light years, I think. Yes. And not surprisingly, as we go back in time to the right, or out in redshift to the right, what we find is that there was less and less stellar mass because fewer stars had formed. Okay, and it drops actually by a big factor. You can see it's about 100 times lower back at the right side of this plot over 12 billion years ago, getting close to the Big Bang. What's really remarkable to me about this is, well, it's really neat that we can make this measurement. And this is almost all Spitzer data that was used to make this measurement. But what's really remarkable is that black line is not a fit for these data at all. That black line is just the same black line I showed in the previous slide, converted into stellar mass. And so if you know how fast stars are forming at each point in the history of the universe, you can say, well, okay, we're forming stars at 10 solar masses a year. After a year, we're going to have 10 solar masses. After 2 years, we'll have 20 solar masses, and so on. And you just add that up, and you get this black line, which gives you the stellar mass over the history of the universe. And so these two measurements actually, amazingly to me, agree with each other remarkably well. And so this really gives some confidence astronomers might actually know what we're talking about here when we talk about the star formation history of the universe. And Spitzer's really been central to this. So I'm going to close with a view of the most distant galaxy that we know about, which is not a redshift 2 or 4 or 8, but actually 11.09 in fact. It's so far away that, as I said, it completely disappears in visible light. And we're looking so far away that we're looking to when the universe was only 400 million years old, which sounds kind of old, but it's only 3% of the age of the universe today. So it's really, it's infant years. And so here is an image, not just in visible light where it doesn't show up at all, but even at 1 micron from the Hubble Space Telescope, pretty deep exposures. You don't see much of anything. You have to go all the way out to the longest wavelength that Hubble can observe at, which is 1.6 microns. And this is, by the way, in the James Webb wheelhouse, these kind of wavelengths. And there it pops up nicely. And what's happening is that the light has been redshifted, expanded so much that we're looking far, far into the ultraviolet wavelengths, less than 1/10 of a micron, until we get out to 1.6 microns here on Earth. That light started out at about 0.1 microns, 0.12 microns in the galaxy. Now, that's still far in the ultraviolet. If we want to have some idea what this galaxy is doing, we want to see something like visible light, and that's what Spitzer can do for us. And here we see it just comes booming through in a admittedly 100-hour exposure. Actually, I think it might be 200 hours for this particular galaxy. But the thing is that, so Spitzer's seeing it, and so first of all, it's telling us there's not just a blip here, there's actually really something there. This isn't just a mistake. There's actually something there, which is good to know. I wrote a paper once on a redshift 10 galaxy that turned out not to be there. Actually, the paper was on the galaxy not being there, which didn't get much attention. People don't want to hear that.
That's right.
But Spitzer's reaching out almost into the visible range. This redshift is so big that even at 4.5 microns here, we're only getting to the light that's a bit bluer than our eyes can see. But still enough into the visible that we have some idea of what this galaxy is up to in terms of its age and its mass. It's surprisingly massive, given that we're looking so far back and close to the Big Bang. And maybe not surprisingly, it's not very old, less than 50 million years. Okay, and all of this is exactly the kind of galaxy that the James Webb Telescope was designed to go after. And yeah, that's a big one. Those are real people standing there in the, I believe it's the thermal vac chamber in the Johnson Space Center in Houston.
And I love the size of that door.
Yeah, yeah.
Yeah.
And so I was talking to John Mather at the American Astronomical Society meeting, and he said things are going pretty well, but there's still another year before James Webb hopefully launches, and hopefully all the complicated things that have to go right will go right. And there are a lot of them, so there'll be a lot of tense moments there before this is fully deployed. But it very exciting times, and Spitzer has really played a tremendous role in, first of all, showing that there are galaxies that will be straightforward and exciting for James Webb to study, and maybe more importantly, finding, because of its ability to survey large regions, where some of those best targets for James Webb will be. Because James Webb is extremely powerful, but it's a bit of a battleship, and repointing it takes a while. And it can't map out large regions. And Spitzer, in contrast, is mapping out quite substantial regions. And so we've done our biggest survey ever, taking the better part of a year of Spitzer time, picking out the galaxies that will be best for James Webb. And so I want to close by thanking you for listening, and of course we're happy to answer questions, and we'll be signing copies of the book, and we don't get any royalties, in case you're wondering. But I really want to close with this epigraph from that sort of brings us back to the beginning. With that Redshift 11 galaxy, I think we might agree that Spitzer has brought us very close to the first light in the universe, and that inspires this epigraph, which is near the end of our book. What we call the beginning is often the end. We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time. Thank you.
Thank you. Now, I know that people probably have questions, and I have questions. However, the bookstore is only open for 10 more minutes. And I'd really like to have, I think that you've seen, obviously, the wonderful quality of this presentation, the amazing stories that are told in the book, and I will encourage you all to head out to the book shop and pick up a copy. I see some people have one already in your laps, but so let's do the signing now, and then we can have any individual questions either at the table with them or in here if you so
Sure.
desire. So thank you everyone for coming. I just wanted to say that whole star formation history of the universe and using ALMA to look is the subject of our next All Space Considered. That's the research project we did with the Cosmos people. So
Yeah.
part 2 to
Well,
come.
I want to thank Laura and her staff for hosting us here.
Oh, well,
It's
thank
been a
you,
real
Mike.
pleasure to be here.
Thank you so much for
I'm
coming.
embarrassed to say I've lived in Pasadena for 30 years. This is the first time I've been here. It is embarrassing, isn't it?
So good night, everyone. Thank you.
So shall we go out to the table?
Yes, please
Okay.
go out to the table and.